In our last video, we looked at an introduction to the system of units that we're going to be using in this class and are generally used internationally in science, and that is the SI units, or System International. In this video, what we're going to look at is the standardization of units. How do you define a unit so that you can get a reproducible standard each time that measurement is recreated? And as a quick reminder, right, we'll look at the 7 base units in the SI system, and these are things that you definitely need to make sure you take down as notes, and you need to kind of keep in your head as kind of the foundation of the system. So we have 7 base units: kilogram, meter, Kelvin, seconds, moles, ampere, candela. Those are all of the units that must be standardized or defined. You have to have a way to recreate those measurements because the entire system in SI is built on these 7 base units. Every other unit, any possible thing you could imagine measuring, is going to be some combination of these units, or what we refer to as derived units. So what is a standard? Well, a standard is, as I have just said, a definition, a reference point that you can use to recreate a measurement, and so that it's recreated the same every time. And what do we need out of a good standard? Well, you want it to be reproducible. You want it to be the same every time you get it. You want it to be fairly accessible, meaning that you want anyone, anywhere to be able to recreate that standard. So as we do science in different places across the globe, we can communicate those results, and we can be certain that that communication has some validity or ability to compare, because the units are the same. They should be independent, meaning you should be able to define a unit without some reference to another thing that has to be defined, and we'll come back to that. And you want them stable over place and time. All right, so we're going to look at a couple of examples of how different SI base units have been defined over time. We're not going to go over all 7. These things are pretty easy to find if you Google them. We're going to look at specifically the meter and the kilogram, and then we might look at a couple others just as comparison. So let's start with the meter. Initial attempts to standardize the meter in the late 1700s were to define it as 1/10,000,000th of the length of a quadrant of an Earth meridian. So there are, of course, 2 lines on any map or globe that allow us to identify a position on the globe, and those are lines of latitude and lines of longitude. The lines of latitude are often also referred to as parallels because they're equidistant apart all the way around the globe. They never cross. And the lines that go from North Pole to South Pole are often referred to as meridians, and you may be thinking in your head about the prime meridian, which is the line of longitude we use to establish standard time. All right, so this is a good standard for a couple of reasons. One of them is that it's accessible. This reference to a quadrant of an Earth meridian essentially means 1/4 of a line of longitude. And as long as you know how long a line of longitude is, then you can go back and you can take 1/4 of that and you can find a meter. And this is fairly accessible because anyone can sort out the circumference of the Earth and thereby get a roughly the length of a meridian with some very simple tools. Now you may be thinking, 1492, right? I say that and it should immediately pop in your head, right? Columbus sailed the ocean blue. And one of the great fears in Columbus heading west to try and find a trade route to Southeast Asia is that people thought he might sail off the edge of the Earth. And it turns out no intellectual at the time was very concerned about that. What they were concerned about is that Columbus was really bad at math and that he would run out of food long before he would reach India. And he certainly would have had he not bumped into a continent that he died thinking was India and nearly ran out of food getting to that little stop that he was unprepared for. But again, the reference to knowing the circumference of the Earth, going all the way back to a couple hundred BCE, the Greeks had sorted out the math to figure out the circumference of the Earth, and they well knew that it was a sphere and that it was not flat. Eratosthenes is often credited with this calculation, and essentially what he did is he measured the distance between two cities, Alexandria and Syene, and in one of those cities was a well, and he waited for the sun to be at its highest point in the sky so that light shined directly down the well without shadow on the side. And then in Alexandria at the same time, there was a tower or a pillar where he measured the length of the shadow on that pillar. And because the Earth is curved, rather than shining straight down on the pillar, it shined at an angle, even as it was shining straight down the well in Syene. And so if you measure the angle between the shadow and that pillar, you get this little angle that you apply just a tiny bit of geometry. You have opposite interior angles of parallel lines cut by a bisector, and you can figure out the angle of the arc length between those two cities. And if you know the distance between those two cities, it's some fairly simple math to go from an arc length and an angle to what would be the arc length of 365 degrees all the way around. And those estimates were really, really accurate. And so using a portion of an Earth meridian to standardize a meter is pretty good, except when we talk about that necessity for a good standard to be stable, the Earth is not a perfect sphere. It's an oblate sphere. It's squished. And so no two places are going to have exactly the same distance because of the lack of the Earth being a perfect sphere. And so this standard has some good things to it, but it's not a perfect standard. And so throughout history, we're constantly just trying to redefine these standards in meaningful ways. And so in 1889, we established the standard as, and I've got some slide issues there. Go ahead and click through again. In 1889, we reestablished the standard as the international prototype made of platinum and iridium. Essentially, we made this funny-looking bar here, cut it to be what we were going to standardize a meter to be, stuck it in a museum. So we have a couple of things going on here. It's fairly stable. You can always go back and measure your meter against that platinum iridium alloy, but it's not very accessible. You would have to travel across the globe to the museum where they're holding the international prototype anytime you wanted to standardize your meter, and that's problematic. Also, metals expand and contract with temperature, so you need a whole other set of conditions telling exactly what temperature that bar of metal would need to be measured at in order to be exactly a meter. So this held up for a while, but then in 1983, which was our next big revolution in measuring the meter, we defined it using lasers and computers. So we have a laser emitter, we have a laser receiver. You shoot the laser, you wait for the receiver to pick it up, and the computer will then measure how long that takes. And then you move your receiver and your emitter to the exact right distance so that it takes 1/299,792,458 of a second. So we've defined light, or the meter, in terms of how long it takes light to go a certain distance. The problem with that is independence. Without defining the second, you can't define the meter. And so you also need to know the speed of light, which has to be measured, knowing what a meter is. But this has some usefulness in terms of accessibility. Any lab across the country that has a laser emitter receiver connected to a computer, which is many, many labs, can recreate the meter. And so we'll come back to this definition of meter here in a little bit. Now what I want to do is go to the kilogram. The original definition of the kilogram was the mass of a cubic decimeter of water. A cubic decimeter is about a liter. So half of a 2 liter of soda is what you would define as a kilogram. This is great except for the fact that, again, the density of water is temperature dependent. So you would need another set of conditions here for that to be a good standard for a kilogram. So much like the meter, And around the same time, in 1889, we defined it as the mass of the international prototype of a kilogram made out of platinum and iridium alloy. So you can see in this picture a bunch of bell jars, and in the center is this hunk of metal. And this was in a museum in Paris. And then they made a bunch of different copies, and they sent them around the world to be held in other museums so that you didn't have to travel all the way to Paris every time you wanted to confirm that your kilogram was in fact a kilogram. And what's interesting is when they did this, they made a plan to bring all those kilograms back together, to recalibrate them, as it were, or at least check on them after a certain period of time. And it turns out, and we have a nice little graph of this here, that no 2 kilograms weighed the same. And so here's a graph that goes all the way into the late 20th century that shows you what's called the mass drift, or the difference in mass relative to that initial standard after a certain amount of time. And the real problem with this is you don't even know whether or not the standard maintained the same mass. So either this original prototype is no longer a kilogram, or a kilogram is not what it used to be, and there's no way to confirm that. You cannot confirm that your kilogram has even really changed because you don't know what a kilogram is anymore. And so this is a huge problem, as the kind of the foundational bedrock of science is that you can measure things, and we don't have a way to measure a kilogram. And so, again, we'll come back to this in just a second. I'm going to give you one more example of a standard, and that's for the ampere. The ampere is the measure of electric current, and it's defined as this. The ampere is that current which, if maintained in 2 straight parallel conductors of infinite length of negligible cross-section and placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 times 10 to the negative 7 newtons per meter of length. That is a mouthful to go through there. And what you're really seeing there is if you run an electric current through a wire, you will also create a magnetic field around the wire. And if you put 2 wires that have a current going through them close to each other, depending on the orientation of the current, they'll either repel or they will attract. And you can measure the force with which they do that when they're 1 meter apart. But you have to be able to measure that force. And the force in the SI system is measured in a thing called a newton. And a newton is, in base units, kilograms meters per second squared. So in order to standardize a kilogram, you need a couple of things. First, you need 2 wires of infinite length. That seems like that's going to be problematic. In practice, you use 2 really long wires because at any point where you measure the force, relative to that point, the wires might as well be infinite, or at least the force will be about the same. But then you also need to know what a kilogram is. You also need to know what a meter is, and you also need to know what a second is. So that's not particularly dependent. And if we go back and we look at all of these standards, what we find is that every single one of them suffers from the same basic problem. Standardizing units is hard. And so we're constantly looking for new ways to sort this out. Well, for the last handful of years, really decades probably, the international scientific community has been wrestling with this problem. And they came to the conclusion for how they were going to fix this very recently, just within a little over a year. So on May 20th, 2019, they completely changed the approach to the system. And rather than trying to standardize units in order to define or measure, I should say, various universal constants, they instead chose to standardize or fix the constants. We've been trying to measure them for years, and we've gotten really, really accurate at measuring them. And so what they've done is they've gone out to a fair number of decimal places. They've cut off our estimation of those values, and they've said, this will be the fixed speed of light. This will be the fixed charge on an electron, and we will sort out what the base units are then relative to those constants. And so this is how they fixed the kilogram problem. It's defined by taking the fixed numerical value of Planck's constant, which is a feature of energy in the universe, and particularly the electrical energy, and a thing called a watt balance. That's the picture that you have in front of you there, that big metal contraption that the scientist there is working on. And what you do is you run an electric current through that thing to, again, generate a magnetic field, and then you're going to put a metal mass in there that is supposed to be a kilogram, and see how much magnetic force it takes to hold that kilogram up. And that will give you a measure relative to the energy it took to do that of Planck's constant, which you can then back calculate to find what the mass of a kilogram is relative to Planck's constant. That big number in the middle of the page here is Planck's constant, and its units are joules times seconds. A joule is a derived unit. Again, it's a combination of kilograms, meters, and seconds. So if you take joules times seconds and convert it to base units, you get kilograms meters squared over seconds squared. That s to the minus 1 means in the denominator. Okay? And so you have now this way to measure Planck's constant and then back calculate a kilogram. And this is a really, really effective way for standardizing the kilogram. But there's a certain degree to which this is cheating a little bit. We needed to standardize units in order to figure out the values for these constants. And once we did that, we decided to fix the constants and then back calculate the standards. But there's nothing to say that that constant is exactly that value in the universe. But if you look at how many digits we've taken that estimation out to, it's going to be good enough to do any science you need to do. And it rids ourselves of the kilogram problem, at least if we don't look at it too hard. You'll also see down in this picture in the corner what's called a perfect silicone sphere. That is another way they use to cross-reference the mass of a kilogram, because there's a way that they can figure out exactly the number of silicon atoms in that sphere. And once they know the number of atoms, then they can use what's called Avogadro's constant, which we'll learn about way later in this class, to figure out what a kilogram would have to be relative to that sphere. So they have two different methods that they can use to cross-reference a kilogram. And again, as long as you don't look too close, this is probably a good enough solution to our problem. And so if we go back here and we look at the 7 base units in the SI system, they're no longer 7 base units. Well, there are, but there's 7 base constants first. We define the constant, and then we define the unit. We're going to learn about Avogadro's constant, which is number 6 down there. Obviously, the speed of light is how fast light travels in a vacuum. The rest of these things, you don't necessarily need to know what they are. I should say probably number 4 we'll look at it as well, because that's elementary, or the elementary charge is just the charge on an electron. What's the charge of a single 1 minus or single 1 plus? And that is something we'll come back and take a look at. So if we look at these constants, and I just want to pick out this one, the speed of light, because that's how we now define a meter. If we know exactly the speed of light, we can measure how long light takes to travel that distance in 1 over 299,792,458 of a second. If we fix the speed of light, then we can go back and find how long a meter is. Down here on the bottom are just a couple of extra points. One is the most probably recent published paper on trying to measure the speed of light in the lab is a slightly different number than we've standardized it to. And so, again, fixing the speed of light is not saying that that is exactly the speed of light. It's saying that for calculational purposes, we are going to say that the speed of light is exactly that number, and then we can always work backwards to find our units. The speed of light is given the variable c, by the way. That comes from Latin celeritas, which means swiftness, and light does in fact move pretty quickly. So we'll stop there. That is kind of an overview of measurement standardization, and we're going to use that to understand how we go in and take these units to measure things in the lab.